Hello class. So this is video 2 on section 5.4. In the last video, we talked about what even and odd functions are. We gave an algebraic and a graphic definition. And then we saw in our theorem that what does this tell us whenever we're integrating an even or an odd function about a symmetric interval, or something that looks like negative a to a, then we get some shortcuts. Basically, if your function is even and you're integrating from negative a to a, it's the same as just integrating from 0 to a and multiplying by 2. If your function is odd and you're integrating from negative a to a, it just becomes 0. And we drew pictures of both cases, right? In the case when we have something that's even, when we have something that's odd. Now let's do an example. This is going to be not really that complicated, but it should basically go through everything that that we talked about in the previous section, in the previous video. So we want to evaluate this integral using symmetry. So notice that here we're on a symmetric interval, right? So we're going from negative pi over 2 to pi over 2. So it's negative a to a, where a equals pi over 2, and we want to use symmetry. So at first, we have a sum of different functions. So let's first separate it. Right? Remember, that's one of the properties of definite integrals. You can separate whenever you are adding or subtracting. So we have cosine 2x dx plus the integral from negative pi over 2 to pi over 2 of cosine of x times sine of x dx, and then minus the integral from negative pi over 2 to pi over 2 of, actually let's take out the 3. So we can move out the negative and the 3. That's another property. And whenever you have a constant multiplying the function, you can move it outside the integral of sine of x to the 5th. Now, we want to use symmetry, meaning that we want to identify whether each of these functions here are even or odd. Right? So let's go ahead and do that. So let's start with cosine of 2x. I want to check if this is even or odd, right? So let's call it f of x. So let's just go through the property. So let's plug in negative x. So I'm going to do the algebraic property instead of graphing because it's going to be faster. So f of negative x is going to be cosine of negative 2x, versus plug in a negative for x. And then cosine is even, right? Meaning that whenever you have a negative on the inside, it disappears. So it just becomes cosine of 2x, right, which is the original function. So we plug in negative x, and we get f of x, the original function. So cosine of 2x is even. Okay. So it's the first function we had. Now let's look at cosine times sine. So let's do cosine times sine. So g of x be cosine of x times sine of x. And again, we do the same algebraic check. We plug in negative x, simplify, and see what we get. So g of negative x is plug in negative x wherever you see x. So cosine of negative x times sine of negative x. Now cosine, again, it's even, so the negative disappears, but you get the original function. And then sine is odd, so negative goes outside. So times negative sine of x. Right, simplify. Which of course, we have a negative times the original function. So this is the same as negative g of x. So we plug in negative x, we get a negative g of x, meaning that this is an odd function. Okay. Finally, right, the other function was sine of x to the 5th. Oops, so let's go up here. Sine x to the 5th. So let's call it h of x. H of x equals sine of x to the 5th. And again, we do the same check. Plug in negative x and simplify. It's going to be sine of, so actually let me use bracket here, of negative x to the 5th. Now, we're multiplying negative x by itself 5 times. Right? So how many negatives do we have? 4 of them cancel out. We have 1 left over. becomes sine of negative, and of course we have 5x's, so negative x to the fifth. Again, sine is odd, meaning that the negative inside moves to the outside. So here we get negative sine of x to the fifth, and then of course this is the negative of the original function. So it's negative h of x. So this function is odd. And again, that's how you work stuff like this, right? That's the property. You just plug in negative x, simplify, you check whether you get the original function or the negative of the original function. What does that mean about our integrals? Well, simple. This one was odd, this one was odd, this one was even. So if we can rewrite this as, for the even part, cosine of 2x, since this function was even, the integral from negative pi over 2 to pi over 2 of cosine 2x dx is the same as twice the integral from 0 to pi over 2 of cosine of 2x dx. Plus, well, cosine x sine x was odd, right? So whenever you're integrating an odd function on a symmetric interval, that becomes 0 immediately. Minus 3 times, well, sine x to the fifth was another odd function. Whenever you're integrating an odd function in a symmetric interval, you get 0. So this whole thing basically simplified to twice the integral from 0 to pi over 2 of cosine of 2x dx. And everything else is 0. And then here we can use the fundamental theorem of calculus, right? Because cosine 2x is continuous everywhere. So it's continuous on the integral 0 to pi over 2. So what is this going to be? Right, we can worry about the 2 later. Well, we need an antiderivative. So what's an antiderivative for cosine of 2x? And we did this in section 4.9. If you don't remember, it's fine. So we know that the derivative of sine is cosine. So it makes sense to consider a function that looks like a constant times sine of 2x. Again, an antiderivative is a function whose derivative is the little function f. In this case, we're looking for a function whose derivative is cosine 2x. So let's see what we get if we differentiate this function. So c is a constant that stays outside. By the chain rule, this would then become 2 times c times cosine of 2x. So we have almost what we want, but this 2c here should be equal to 1, right? Because here we have 1 on the front, which means you can just let c be equal to 1/2, because then 1/2 times 2 cancel and you get 1. So what's an antiderivative? Well, it's 1/2 cosine, sine of 2x. And again, we did this in section 4.9. Another way you can think of this is when you do the derivative, you're going to get a 2 coming outside by the chain rule. So you want to get rid of that 2, so just multiply by 1/2. That's all we're doing. So by the fundamental theorem of calculus, what do we have here? Well, we found an antiderivative. It's 1/2 sine of 2x. And remember the notation, we do vertical bar, 0 pi over 2. What's this equal to? Well, what this was is still, we have the 2 outside. We can worry about that until the end. That means you evaluate this function at pi over 2 and subtract what you get when you evaluate at 0. So what do we get? We get 1/2 sine of 2 times pi over 2 minus 1/2 sine of 2 times 0. So what do we get? We get 2 times pi over 2. So let's go to another slide. So we had 2 times 1/2 sine of 2 times pi over 2 minus 1/2 sine of 0, 2 times 0. So what is this equal to? Well, 2 times pi over 2 is pi. Okay. So that simplifies to pi minus 1/2. Sine of 2 times 0 is 0, so sine of 0. Now, if you remember the unit circle, both sine of pi and sine of 0 are 0, meaning that this becomes 2 times 0 minus 0, which is 2 times 0, which is 0. So what does that mean? Well, our original integral, let's see, which was this whole thing here, we simplified it to this, right? And then it turns out that so we simplified it to that, which is equal to that, and this we found was 0. This was the work we did here. So the original integral is just 0. So let's go up here. We're just going to write this whole thing equals 0. So of course, this is a long example, but I think if you understand what we did in this example, you understand everything. We had 3 different functions. For each, we checked algebraically whether they're even or odd, and used that to simplify. Okay. So that would be it for even and odd functions. Again, you don't have to do these tricks, but it simplifies the work. Specifically here, right? Those 2 integrals here just became 0.